Afternoon and welcome. My name is Daniela Bortoletto and I'm the head of particle physics here in Oxford. Today's lecture focuses on understanding the ghost particle, highlighting Oxford's contribution to neutrino physics. Neutrinos are one of the fundamental particles in nature. Wolfgang Pauli postulated the neutrino in 1930 to explain how beta decay could conserve energy, momentum, and angular momentum. At the time, scientists thought that neutrino might never be detected. They're neutral, incredibly tiny, and they rarely interact with other matter. But they're also the most abundant particle with mass in our universe, and therefore they play an essential role in cosmology and the formation of galaxies in our universe. Neutrinos are particularly intriguing since many unanswered questions surround them. This puzzle includes why their masses are so small and whether they are responsible for matter's dominance over antimatter in our universe. Oxford has played a unique role in understanding neutrinos. And one of the pioneers was Don Perkins. As you will hear later on, in the 70s, Don made important pioneering discovery during a bubble chamber at Cern called Gargamel. He found hints of neutrino oscillation with the Sudan experiment at the Sudan mine in Minnesota in the US. Oxford has played a significant role in many other experiments that elucidated neutrino oscillations, including SNO, T2K, and Supercamiocanda, that were awarded the 2016 Breakthrough Prize. Several Oxford faculty members, including today's speakers, accompanied Art MacDonald to Stockholm in 2015 when Art receives a Nobel Prize for elucidating neutrino oscillation using heavy water with the SNO experiment. We are now continuing to understand the ghost particles with huge international projects, Supercamiocanda in Japan and Dune in the US. Today, we will start our journey with Steve Biller, a professor of experimental particle physics and a senior fellow of Mansfield College. Steve got his PhD from the University of California, Irvine, which was neutrino land when he was there, with Fred Rains, who discovered neutrinos, and Herb Chang, his advisor, who developed SNO. He came to the UK after his PhD, first at Leeds and then in Oxford, planning to stay a few years before going back to the US. Dave Wark, who will talk next, convinced Steve to apply for a faculty position in Oxford. And now, nearly 22 years ago, after that, Steve is still in the UK. He has been the UK spokesperson for the SNO experiment and is now the UK spokesperson for SNO+. Steve will talk about SNO, a seminal experiment in Canada studying neutrinos from the sun, which found for the first ambiguous proof that neutrino can transform between different varieties, demonstrating that neutrinos exist as mixed state and have mass. Today, using techniques developed at Oxford, a variation of that experiment pursues a new and even more challenging question. Do neutrinos transform into their own antiparticles? Such a discovery could have a profound implication for the origin of neutrino mass, and it could explain the matter-antimatter asymmetry of the universe and ultimately our existence. Steve, I pass the baton to you.
Okay, hi everybody. In Oxford we have SNO and we have SNO+, and so I'm going to tell you a bit about those. But really this is the story of the neutrino. And as Daniela just mentioned, really that sort of starts back in the 1930s for a puzzle that was sort of seen when certain atoms were observed to undergo a radioactive decay process. What was happening there was that the neutrons inside these atoms would sometimes turn into protons and emit electrons. And in such a process, the electron should have a very well-defined energy that you can sort of measure and determine precisely. So this is a process known as beta decay. And when you look at the distribution of energies that people measured, they didn't see the full energy of the electron that was expected, but a distribution of energies all a bit less. And this led Wolfgang Pauli to postulate that what's happening is that some of the energy is being carried away by a ghost particle, an invisible particle that you can never detect. And so this was an uncomfortable hypothesis that seemed to be at the time the only way out. Neutrinos are indeed everywhere. They are produced in the fundamental fusion processes that power the sun, in the radioactive decays that heat the Earth, in nuclear power stations. They are the most dominant source of energy coming out of supernova explosions. They drive the explosion. And there are cosmic ray interactions happening above us, entering in the atmosphere, which is producing loads of neutrinos. Neutrinos are present in the radioactive decays all around us and inside of us, and they are, as Danielle also mentioned, one of the most, largest number of particles of the universe, especially ones with mass, are neutrinos. So here's where they are in the standard model. So this is the most successful model of fundamental physics, and these are the fundamental particles, and so neutrinos are amongst the most fundamental here. There are three types, and they are named after the type of particle they tend to produce when they interact. And so there are electron-type neutrinos, muon-type neutrinos, and tau-type neutrinos. And they're all sort of quite distinct, and they hang together, and everything that we know is sort of made up one way or another from these sorts of particles. But we also now know that neutrinos stand outside of the standard model. They have mass, and this is contradicted by predictions of the standard model. The nature of neutrinos is such that you shouldn't be able to produce mass through the standard Higgs mechanism that many people have heard about that imparts mass to other particles. It doesn't seem like it should work for neutrinos. And in general, the mass of neutrinos just looks very, very different from the masses of the other fundamental particles. So it looks like something else is going on here. So we have this very successful...
Steve, I just wanted to tell you that your slides are not advancing. We are still in the title slide.
Oh, I have been. I'll go back. Can you see my slides? Sorry, I was sort of talking about this sort of process of beta decay that Daniela mentioned, where you expect to see the full energy, but you only saw a bit, and so the neutrino was hypothesized. And neutrinos can be sort of seen everywhere in the sun, in the Earth, in supernova, and everywhere around us. So here they are in the standard model, but we now know that they also stand outside of the standard model, in that they have mass, which is not predicted, which does not seem to naturally result from this, and this mass seems to be fundamentally different than other things. In addition to that, we know that aside from the standard model, there is a dark side to the universe. This is dark matter and dark energy. And we don't really know what this is, but it may indeed also be associated with neutrinos. So the standard model right now looks a little bit worse for wear. But this is exciting for us because we want to get through that wall and see what's on the other side and improve our fundamental understanding of things. And neutrinos look like a good tool to do this. But I just said that before that neutrinos, they were thought to be impossible to detect. If you look at at how much detector you would need, what you would need to stop a typical neutrino produced in a nuclear decay, you would need several light years of lead. And so it sort of seems it's totally impossible right from the beginning. So the only way to go about this is really to play a numbers game. You look for an intense source of neutrinos, you build as large a detector as you can manage, you put it, you sort of wait for a long time, and every now and again, by just dumb luck, neutrinos will interact with your detector. So the chance of sort of seeing any one neutrino from a decay, impossible, forget it. You can't sort of think of any practical way of doing it. But the odds of sort of seeing something once in a while from just sort of dumb luck, if you look at enough of them, that's the only game in town. So that's the game we play. One place where you see lots of neutrinos is the sun. Just from the fundamental fusion reactions that power the sun, there's something like 100 billion neutrinos going through your thumbnail every second. And yet the odds are only a handful of these may interact with your body during your lifetime. But there's loads of neutrinos there. And so if you build a large enough detector in a quiet enough place, again, using the dumb luck approach, now and again, you can see these. Several of the earlier experiments that sought to find these neutrinos and sort of understand test our understanding of how the sun works came up short. So here are sort of three different techniques, and theoretical predictions are represented by the tops of these colored bars, whereas these blue bars represent different experiments that look to measure neutrinos, and they all came up short by a factor of 2 or 3. And it's turned into more and more of a problem to really understand as time went by. And so the SNO collaboration was formed. SNO stands for the Sudbury Neutrino Observatory, and involves a number of universities from Canada, half a dozen places from the US. And at the time, just us here in Oxford, our group, but we played a really fundamental role in this experiment. So that experiment was located here over in Sudbury, but Sudbury, Canada. It's about an hour's flight north of Toronto. And this brings me to my favorite postcard. The red hot slag pouring is a Sudbury landmark. Unfortunately, you can't see the slag pouring now. So you know, quieter nights in Sudbury. But here we are near the top of the experiment. This is the mine shaft you go down to get to it. And you can see another reason why SNO is an appropriate name for it. You travel down about 2 kilometers down a rickety sort of lift that goes down the mine shaft. You emerge at the bottom and you walk for about another 20 minutes until you get to our high-tech underground laboratory. Sorry, that's the laboratory next door. Ours looks more like this. And the detector, which is underneath all of this mass of pipes and electronics, looks sort of schematically something like this. It contains at the center of it is this sphere, which is sort of acrylic, about 12 meters in diameter. And inside that acrylic ball is heavy water, about 1,000 tons of heavy water that we borrow from the Canadian heavy water nuclear reactor program. And so the point of using this is we have a lot of sensitive light detectors all around the outside, and we can sort of look for characteristic signatures of 3 different types of reactions. So one of these is only sensitive to electron neutrinos, which is the only type that can be produced in the sun. What was fundamental and sort of different about SNO was our ability to see this central reaction as well, known as neutral current, which gave us sensitivity to all types of neutrinos, whatever they are. And this is the reaction, neutral current, as Danielle mentioned, that Don was sort of fundamental, played a fundamental role in discovering this at Gargamel, as Dave and Brian will sort of mention. And we were wildly successful. We had, as newspapers as far afield as Wolverhampton will attest, we indeed solved the problem. And the solution was interesting. And it has to do with the fact that if you just look at electron neutrinos, you see the shortage. But if you look at all types of neutrinos, you see exactly the right number. But we know the sun can only produce electron neutrinos. So this is clear evidence that electron neutrinos were produced, but they somehow changed in the process of traveling to us. They're able to sort of transform to some extent into the other types of neutrinos that our experiment was able to see, but others couldn't see. So this is sort of big news and helped establish the fact that neutrinos have mass, which again puts this in this interesting class of being beyond the standard model, and a whole industry is really sort of opened up, people looking for this and trying to understand all of this a lot more. And indeed, this resulted in the 2015 Nobel Prize awarded here to Art McDonald, who was the Canadian head of the project, for the discovery of this known as sort of flavor transformation or neutrino oscillations, which also showed that neutrinos had mass, all of which totally unexpected by our understanding of the standard model. And as a result of the fundamental role that Oxford played in this, myself and Dave and another colleague of ours, now retired, Nick Jelly, were amongst a handful of people that got to accompany Art on this trip to Stockholm in December 2015, where we had a nice meal. Unfortunately, my daughter was a bit less pleased by the whole affair because all she got out of it was a stupid novelty hat from Sweden. And so when Art, after he got his Nobel Prize, the very first place he stopped off on the way back from Stockholm was here in Oxford, where we had another Nobel banquet. There you can see between myself and Ian is Don Perkins. And so it was really a great evening. Great way to wrap up the year. Okay, so where do you go from here? Well, you go on to ask even bigger questions and more difficult questions and more difficult experiments to try to answer them. When the universe was created, it must have created an equal amount of matter and antimatter, but then that should have annihilated, leaving nothing left. So why are we here? And if you look around, there are not large chunks of antimatter about, which is sort of a good thing. So it must have been the case that somewhere, sometime in the early universe, some piece of it was able to sort of flip from antimatter into matter. And that little bit of resulting from the flipping is the thing that survived and allows us to exist today. We don't know what this is, but one thought has been that maybe neutrinos, in addition to being able to sort of flip into their other types of neutrinos, perhaps they can flip into their own antiparticles. They are the only fundamental particle we know that might have this property. And if it's possible, it could start to give us an explanation for the existence of everything that sort of survived this the cataclysmic annihilation. So this brings us now onto SNO+. This is sort of revamping the SNO detector, now filled with liquid scintillator instead of heavy water. And liquid scintillator is a substance that readily gives off light when charged particles pass through. And this is operating now, and in about a year's time, we then hope to add tellurium into the liquid scintillator. And the reason for doing that is that tellurium is is one of the handful of isotopes that can undergo a double beta decay process. So this is a process in which the beta decay we started with happens twice. In both cases, producing sort of an electron and a neutrino in addition to sort of the proton that comes out. But it was recognized that if the neutrinos can flip between particle and antiparticle, then one of these in the process could sometimes flip around, canceling each other out, and then the only thing you get out are the electrons. And so it goes back to that first figure where the puzzle was, why didn't you see all the energy here? Well, if you don't have neutrinos, then you would see all of the energy there. And so that would be this telltale signature that somehow neutrinos are indeed acting as their own antiparticle, canceling each other out and allowing you to see the full energy of the decay. So this is the idea. So the idea for doing this came out of Oxford, and indeed as well as the loading technique for how you get tellurium in, which was sort of a big puzzle just at the beginning. And the reason we're pursuing this is we think it has the potential to be able to be used in even larger detectors in the future. This is a very, very tough experimental challenge. We don't yet know how far we have to go with it before we can see this phenomenon. And so we're already starting to plan for the future and bigger and better experiments to see this. Without going into sort of details, there is this paradigm that has developed over the last sort of several decades that is able to apparently tie together our understanding of the nature of neutrinos, why they have mass and why that mass is different from the others, and this idea of how you get the universe working so that you explain the matter-antimatter asymmetry. It makes two fundamental predictions. One is this, that neutrinos act as their own antiparticles, and that's what was pursued here. And the other is that it violates this fundamental symmetry known as CP. So these are indeed the two areas that Oxford is very actively pursuing. So we're pursuing this bit with sort of SNO+, and Dave will talk about efforts looking at the long baseline neutrinos, looking for CP violation and understanding of that. SNO is SNO+ is a unique detector. And so in addition to looking at this very important phenomenon, we're looking at lots of other things, including neutrinos and their oscillation coming from nuclear reactors, from neutrinos coming from radioactive decays that heat the Earth, and our understanding of how that Earth heating sort of works, more neutrinos from the sun, and indeed studying any neutrinos that could be emitted from supernova explosion, and a host of other things. So really, there's a lot that we're doing with this, and this is also reflected by the diversity and interesting nature of the theses that our PhD students are currently working on. And our students currently work on sort of many different things, and so we are continuing to have a lot of fun with this. and continuing to push the bounds of our understanding from a hole very deep in Northern Ontario. So thank you very much.
Thank you, Steve, for this very fascinating journey to Snow Lab and to this beautiful experiment. Before taking any question, I will actually continue with the second speaker, and we will take actually question at the end of the session. The second speaker today is Dave Wark, an internationally known physicist for his work on neutrino properties. Dave started to work in neutrinos at Caltech in 1981, meaning that he has been studying these fascinating ghost particles for 40 years. He joined SNO as a postdoc at Los Alamos before moving to Oxford in 1990, where he became a tutorial fellow at Balliol. He loves Balliol as much as he loves neutrino, I think. Dave took a brief break from Oxford to work at Rutherford Appleton Laboratory, where he became director of the particle physics department, but is now back in Oxford and in Balliol. He has worked on many neutrinos experiments, including pioneering the pattern recognition techniques, which were an early version of what is now called machine learning for neutrino physics and for the Nobel Prize discovery of neutrino oscillations. After SNO, Dave started the UK effort in T2K. He became the international co-spokesperson of T2K and is now the UK leader for HyperK, the Supercamiocanda experiment. He won the IOP Rutherford Prize for contribution to astroparticle physics in 2004, and he was elected to the Royal Society, a fellow of the Royal Society in 2007. Dave will take you to the next part of this journey, to long baseline neutrino experiments, where neutrino beams created by accelerators are measured very far away in huge detectors. Don Perkins played a pioneering role in inventing such accelerator beams, neutrino beams. Now we use these neutrino beams to study neutrino properties and probe fundamental questions such as what is the pattern of neutrino masses, and do neutrino and antineutrinos oscillate in the same way? Both these questions are of profound importance to fundamental particle physics, but also to cosmology. They will discuss the critical role that Oxford physicists have played in the discovery already made by long baseline experiment and our role in the exciting plans for two vast future experiments, Dune in the United States and Supercamiocanda in Japan. Dave, I pass the baton to you now.
There we are. There we are. Perfect. Great. So a victory for Windows. Hello, everybody. I'm going to tell you some more about neutrino oscillations, continuing on from where Steve finished, or and pursuing the oscillation side of it. As Steve said, this speculation that perhaps the matter-antimatter asymmetry of the universe arises from properties of neutrinos at very high energies has sort of two low energy predictions, one of which is double beta decay, which Steve is pursuing with SNO+, and the other is that CP should be violated neutrino oscillations, that neutrinos and antineutrinos should not oscillate the same way. And we need a different type of experiment to look at that. And let me tell you about that. But first, before we get to CP violation, of course, SNO had demonstrated the neutrinos oscillate, or rather, SNO had demonstrated that neutrinos change flavor. And when combined with other experiments, it indicates that they oscillate. A neutrino oscillation, mathematically, looks much like a rotation. And a rotation in 3 dimensions, and there are 3 neutrinos, so it's a rotation in 3 dimensions. There are 3 angles involved. So if you think about, pitch, yaw, and roll for an airplane, it's sort of similar to that. And Snow measured one of those angles, but what about the other two? Before we can really claim that the model of neutrino oscillations applies to the data we see from experiment, we have to be sure that we have measured all the different properties of the oscillation. So there are two other angles that need to be measured. So the first experiment that comes into that is Supercamiocanda, which is a vast water Cherenkov detector in Japan. Now, this works by a similar principle to Snow. Charged particles traveling through the water emit Cherenkov radiation, a cone of blue light, which is detected by these very sensitive photomultiplier tubes at the edges. Supercamiocanda's disadvantage relative to Snow was that the water in Supercamiocanda is just regular light water, so it can't see these neutral current events. On the other hand, its advantage is it's vast. It's a right circular cylinder, 40 meters in diameter, 40 meters high. It contains 50,000 tons of light water. And it was built primarily to look for proton decay, a sort of generic prediction of physics beyond the standard model should be that something should couple leptons like electrons and muons to quarks. And whatever that force is, it should permit the proton to decay. And so experiments have been being built since the 80s to look for proton decay. Supercamiocanda was built to look for proton decay. However, it had to study atmospheric neutrino events. Now, the cosmic rays that impinge on our atmosphere produce pions in our atmosphere, and those pions decay, and when they decay, they make neutrinos. And so these neutrinos can penetrate inside the detector and interact and can create charged particles that look like they come from proton decay. So this is a potential background to proton decay. And in the study of that background, the detector had to take advantage of an interesting property, which is that even in a simple detector like this, with just water and phototubes, you can tell muons from electrons. I'll come back later to how that's done, but when they looked at the events in the detector separately, I hope you can see my cursor. This plot shows what they saw for electron-like events as a function of the zenith angle. So this is the angle relative to the ground, right? And so -1 are things coming straight up from below your feet, and 1 are things coming straight down overhead, and 0 are things coming sideways. Remember what Steve said about neutrinos, they barely interact with matter. So you can see neutrinos coming from the atmosphere all around the world. The Earth itself doesn't block any significant number of them. And the electron neutrino-like events look fine. The dots are the data, and the blue is the prediction of the Monte Carlo, the computer program that combines our knowledge of the creation of the neutrinos with their propagation and with the behavior of the detector. Everything looks fine. But if you look over here for the events that look like muons, you see that events coming straight down from overhead look fine. The blue boxes and the dots match. But when you come over here from events coming up from below, these blue boxes are roughly double the points, which tells you this one plot all by itself tells you neutrinos have mass and the standard model is wrong. And the reason is the neutrinos coming up from below know they've traveled farther than the neutrinos coming down from above. And if they know they've traveled farther, they must have a clock which is running. Massless particles travel at the speed of light, and according to relativity, when you're traveling at the speed of light, the clock stops. So their clock is not stopped, and therefore they have mass. And perhaps for that reason, this plot, which is a modern version of one removed from Kajita-san's thesis, won him the other half of the Nobel Prize in Physics in 2015. The red line is a model fit to this, assuming the neutrinos oscillate. And as you can see, it fits the data very well. Okay. So this data certainly gave strong indication that neutrinos oscillate. This is, by the way, how Supercamiocanda can tell electrons from muons, because electrons, as they travel through the detector, what you see here is you see these plots, these circles and rectangles. This is the Supercamiocanda detector, where each of the points is one of those phototubes. And by the way, behind my head in my backdrop is the photograph of the inside of Supercamiocanda, where you can see all those phototubes. Each of these dots is a tube that's been hit by a photon. And you can see the ring that you expect to see from Cherenkov radiation in these events. But when it's electron, electrons are light and they multiply scatter, so the ring gets smeared out in fuzzy. Whereas muons are heavy, so they travel in nice straight lines, and the ring does not get smeared out. And therefore, Supercamiocanda can tell electrons from muons. That becomes very important later on. The indications here are for neutrino oscillations. But of course, before we believe that, we want to be able to measure it carefully. So we want to be able to change the energy and change the type of neutrino and do all the things the physicists do. You can't really do that here because you're stuck with whatever the atmosphere provides. So what you would like is an ability to make your own neutrinos and therefore to be able to control their properties. And that's where Don Perkins comes into this story, because Don had been working at Cern way back when, 60s, and was one of the people that helped build the first accelerator neutrino experiment, whereby protons were collided with a target and made pions, and those pions decay to make muon neutrinos. This device on the left is a so-called Horn magnet, or rather this is the inner conductor of the Horn magnet, invented by Simon van der Meer here, who won the Nobel Prize for inventing stochastic cooling, the thing that enables our modern particle colliders to work. He also invented the neutrino horn. In fact, this picture is taken from his obituary in The Economist, which didn't even mention neutrino horns, but went on and on about stochastic cooling. But if you'll notice, the picture that he's explaining to these gentlemen on his board here is a picture of a neutrino horn. So he invented a way you can make neutrinos in a beam, and then you need to pioneer some sort of large detector. In the case of Cern, that was the Gargamel CF3 bromine bubble chamber. And this was used to discover neutral currents, this entirely new type of interaction, which was critical to the functioning of the Snow experiment. And the paper announcing that discovery is here, and you can see Don's name. He's here credited with Cern, but if you look at that 6, he says he's also at Oxford. And there's another name on here, a name of Gerald Myatt, who's at University College at that time, but then became a member of our faculty here in Oxford, and was one of the prominent people working at Cern for many years thereafter. So this discovered neutral currents, but also produced the possibility to build accelerator neutrino experiments where you have a beam and a distant detector. This was then extended. We had a group working on Sudan II, of which Don Perkins was a prominent member, but also Wade Allison and John Cobb and Barry Brooks and several others. Sudan II was another proton decay experiment, but in the mine where Sudan II was, they built a large calorimeter. You can see here a large iron calorimeter, weighed 5,000 tons, and a neutrino beam was fired from the main injector accelerator at Fermilab, 700 kilometers to this detector, which was called Minos. And sure enough, if you look here, you see the prediction without oscillations is the red curve. And what was actually seen were the dots. And once again, you're missing neutrinos. They've disappeared. And so this was a confirmation of the predictions from the Supercamiocanda experiment. The neutrinos would oscillate, and furthermore, it enabled you to measure the second of those three angles. So that's two angles. What about the third? Well, that's where we come in with T decay. T decay was an experiment, is actually, it's still running, an experiment in Japan, where a neutrino beam was built at the new J-Park facility on the east coast of Japan. And when I say east coast, I mean it, because there's a picture of the facility. This is the main ring accelerator, and that's the Pacific Ocean. And yes, that is the one that had the 20 meters tsunami right here. Luckily, there's a little dune that you can't see in between this and the ocean, and it kept the ocean out of our experiment. We make a beam of neutrinos using the same technique as at Cern, but a sort of an updated, much larger and more powerful version of it. We fire the neutrinos through a near detector, which is actually quite a complex object. It uses the techniques of collider detectors to make very detailed measurements of the properties of the neutrinos before they oscillate. They then propagate for 235 kilometers underneath Japan, 295 kilometers underneath Japan, and then strike that same Supercamiocanda detector, which is underneath a mountain here near the west coast of Japan. And what are we trying to do? Well, first we look for muon neutrino disappearance. So this is the spectrum of muon neutrino events we will see in the FAR, or we were predicted to see in the FAR detector, where we have divided the expectation by, the result, by what we expect to see. And so if there were no oscillations, this would be a flat line across here at 1. And this dip is the signature of neutrino oscillations. Okay, that is the oscillation that comes from the atmospheric neutrino, driven oscillation. And that then would measure that second angle again. However, if neutrino oscillations explain this, and if the third angle is not 0, then you expect to see electrons appear in the detector in the mirror image of this. Where there's a dip here, you expect to see this peak. All right, and of course, the hard part of the experiment is understanding these backgrounds and understanding the precise nuclear properties of these interactions, but I don't have time to go into that now. This is what you expect to see. This, I put this slide up, it's a bit of technical detail, but just as an indication that, when you're doing real experiments, the real world is in there too. So this is us collecting data for a period of here, about 6-7 years. What's shown here is each of these dots shows the power of the accelerator at any given time. And on this axis, you can see the beam power going up to 500 kilowatts. So that's a tiny little beam of protons carrying 500 kilowatts of power. And here you see this axis shows this line. That's the accumulated number of protons on target. So basically our signal goes with that. And you can see that the beam only runs part of the time. That's because in the summer, electricity is too expensive in Japan to run your beam. But then you see these two large gaps. This gap was caused by the Great East Japan earthquake, which turned the roads into pretzels, knocked down many of the buildings, and flooded the entire facility, including the detector and the accelerator. So it took a year to repair that, and only the Japanese could have repaired it in a year. In any other country on Earth, it would have been down for 5. And this was due to another facility on site blowing up their target and shutting down the whole facility. So the real world intrudes as you're trying to do your experiment. But we have been running the experiment now for 10 years, and what did we find? Well, this shows neutrino events in Supercamiocanda, and here are the muon neutrino events, and sure enough, you see that dip. All right, here we haven't divided it by the expected spectrum. So the expected spectrum with oscillations is this blue curve, and you see that dip. So we do indeed see that oscillation. However, if you look at electron-like events, we also see the mirror image of it. Note that the energy scales in these two plots are different, but you note that this peak is right where that dip is, right? So we see the mirror image in electron appearance, okay? And so this indicates that the third angle is also not zero and enables us to measure it. Notice here, we've done another thing, which is because we have an accelerator now, we can just reverse the polarity of the Horn magnet. And instead of looking at neutrinos, we can look at antineutrinos. So we can compare what we see in antineutrinos to what we see in neutrinos. And I'll come back to that in a moment. Okay. So we did indeed see electron neutrino appearance, and hence we measured that third angle. And that's what the experiment was for. And so in some sense, we're done. But it turned out that angle was as big as it could be. In fact, it was a little bit bigger than it was believed it could be. The earlier experiments had perhaps slightly overestimated their sensitivity. And in fact, the angle was as big as it could be. And it was so big that we had so much data that we could do more things. And we could address two still unanswered questions as of that time: is what is the pattern of neutrino masses? And are oscillations the same for neutrinos and antineutrinos, which is this CP violation that Steve alluded to. So what do I mean by patterns of neutrino masses? Well, the experimental data we have as of now is still consistent with two possible solutions. There's this dirty little secret: neutrino oscillations don't actually measure mass. They measure the difference in the squares of the masses. And it turns out that if you just look at the results, there's two possible patterns of the absolute masses that will give you the same answer for the difference in the squares of the masses. There's this pattern whereby the masses increase, M1, M2, and M3 have a mass pattern that looks like that of the charged leptons, like the electrons and muons and the tau, where the muon is much heavier than the electron and the tau is much heavier than either one of them. It probably looks like that, but it's consistent still with the data that it could look like this, where two of them are very heavy compared to the third. And this is called the normal hierarchy, and this is called the inverted hierarchy. The difference between these two is a difference of a factor of 2 in how much mass there is in the universe of neutrinos. So it's very important to determine which of these is true. Now, theorists claim that this is unnatural, and this is the right answer, to which I respond, does that look natural? Nature decides what's natural, we don't. And so, the same theorists, by the way, told us that we would never see this third oscillation because the right answer for the solar neutrinos from their, speculation would make it impossible to observe it on the Earth. So I've learned in my 40 years of neutrino physics that you listen carefully to what they say and then you measure something. So we need to measure that, and that means we need to measure oscillations in the presence of matter, which means we need to do it at higher energies and longer baselines. Okay, so the other thing we're going to do is look for CP violation by looking for the difference between neutrinos and antineutrinos. And in fact, T decay has run even longer than that data I showed you before and has now reached this point. These are the electron neutrino events. The dots are the neutrinos. On the top are the neutrinos. On the bottom are the antineutrinos. The solid histogram is what you expect if CP is conserved, if neutrinos and antineutrinos oscillate the same way. Whereas the dashed lines show you predictions if neutrino oscillations do not conserve CP. And what you see is our data for neutrinos is a better fit to this dashed line, which would imply a very large violation of CP, in fact, maximal violation of CP. And if that is true, then the number of antineutrinos we see should be less than the prediction, and indeed it is. And so this combination has given us some evidence that neutrinos perhaps violate CP. But the statistics, as you can tell from looking at these plots, are still a bit ropey. And of course, neutrino experiments very hard, so you want to see anything confirmed before you believe it. And there is a second experiment called NOVA at Fermilab, using that same neutrino beam that was used for MINOS and a new detector. And it doesn't see this effect. Now, the two experiments are not inconsistent with each other because the errors are still big enough that they could agree on something sort of halfway in between. And all this tells you is we need better and bigger experiments. So we're improving T to K. One thing we did is we drained Supercamiocanda and cleaned the inside. So I got to spend a week in Japan cleaning rust off the inside of a stainless steel wall. So we could add gadolinium to the water, which allows us to see neutrons and gives us a new handle on the interactions. And here's a picture of me down in the bottom of Supercamiocanda. We've also upgraded the near detectors in the beam, but what we really need is a much bigger detector. Okay, and so we're going to do that. Supercamiocanda is here underneath Mount Kaneyama, about 9 kilometers away, underneath another mountain, Mount Nijugo. I can never say that. I thought it must mean something fancy, so I asked the Japanese what it means, and they said, oh, it means Mountain 25. So, yeah, we'll have to pick a better name. We're going to build Hypercamiocanda. And to answer the first question, I don't know what we will call the one that's even bigger than Hypercamiocanda. Hypercamiocanda is 8 times the size of the already ridiculously large Supercamiocanda. It'll have a total mass of 260,000 tons and a fiducial mass of 190,000 tons. That's the thing that's 8 times larger. And it'll have even more sensitive photomultiplier tubes. And using this, we expect to see this kind of data for the new appearance. Whereas rather than the handful of events you saw in that previous plot, we'll have thousands of events. And this should make it extremely clear whether they oscillate or not. Of course, a project of such importance is, people aren't going to just sit back and let you do it by yourself. The Americans have their own version, which is called Dune. It is a new experiment at Fermilab. And we are very strongly involved in this experiment as well and have been since its inception. And there the neutrino beam will be produced from the main injector of Fermilab, but aimed at a different direction, now named west, for 1,300 kilometers. That's that higher energy and longer distance we need to solve the mass hierarchy problem, to find the pattern of neutrino masses. And they're aiming at a vastly more ambitious detector, something called Dune. You don't get a feel for the size of it from this, but this thing is the size of a large building, and it contains 10,000 tons of liquid argon. And liquid argon, when a charged particle passes through it, you can drift the charge out of it and detect that charge on a very fine grid of wires, giving you the ability to reconstruct with almost photographic precision neutrino interactions. So here is a result from a prototype at Cern, where a pion comes in, scatters off a proton, changes its charge, makes a neutral pion, which decays to 2 gamma rays. And you can see every particle just as clear as a bell. If this were in Supercamiocanda, you wouldn't be able to see that proton at all because it's below Cherenkov threshold. So this particle just disappears, and then you see a couple others, and you don't know what happened. So this is an unprecedented ability to look at the events from neutrino interactions. Imagine a detector the size of a building, which has millimeter resolution. That's 10 centimeters. And look at the resolution you have. You have millimeter resolution on these tracks, and a detector the size of a building. So this technique is very ambitious technique, is already working at Fermilab. with us a prototype detector. You can see here's a person for scale, and there's the actual grid of wires being placed inside this tank of liquid argon, and the electronics on the deck above it with our very own Kirsty Duffy, who is one of our students on T2K, went off to Fermilab as a Wilson Fellow and has now come back as a fellow to Oxford. This is a real event in microboon. This is not Monte Carlo, where you see a neutrino comes in and knocks out a proton, and here's the muon recoiling from the neutrino. This is already doing precision physics, as those of you who watch the BBC will have heard recently. And is the prototype for the Dune experiment, which will begin taking data around the end of this decade, as will Hypercamiocanda. So far I've just talked about neutrino oscillations. I just want to mention, I won't go into it. Obviously, given the scale and the you won't get a whole lot of change back from your $1 billion bill from Hyper-K, and you won't get any change back from your $1 billion bill from Dune. And so you ought to be able to do more than just one thing, and they can in fact do many things. In the case of Hyper-K, we will look at, we still think the proton decays, and we're still looking for it. And so this will be the most sensitive experiment ever for that. And we can also see neutrinos from supernova, from ancient supernova. We can see neutrinos from dark matter interactions, from the sun, from the core of the earth, and so on. So there are many, many things, as Steve pointed out, these detectors can do. For instance, this is one that will be, if this happens, this will be amazing. This is the events that Dune will see from a galactic supernova. And you can actually see this huge spike. These are the neutrinos created when you turn a ball of iron into a neutron star. So this is direct evidence that supernova really are produced by the creation of a neutron star. So conclusions, neutrino oscillations are the first laboratory physics we've seen beyond the standard model. They could be way beyond the standard model, we just don't know yet. The parameters of those oscillations are fundamental constants of nature, at least as far as we know. So that's what we do, we measure such things. But the very smallness of the masses of neutrinos, we're looking at masses which are, 1,000,000 times smaller than the mass of an electron. These may be hinting at physics of very high energies. They're the second most numerous particle in the universe that has mass, while they're the second most numerous particle in the universe, full stop. The most numerous particle in the universe is the photon. It doesn't have any mass. So even a tiny mass has cosmological consequences. They may be pointing to the solution of where the matter-antimatter asymmetry arises from. And the detectors we build to study them can study many, many things. So with Dune and Hypercamiocanda, we have enough to keep us busy and happy for a long time. So I'll leave you with this. Thanks.
Thank you, Dave, and thank you, Steve. A virtual clap for your beautiful lectures. We have a ton of questions from the public, even if Steve has been, sort of answering them as you were talking. But really, let's tackle a few of the questions. For example, one quite fundamental one, because we have spoken about neutrino from the sun. And one of the questions was, why are solar neutrino only of one flavor? Steve, do you want to take this one?
Yeah, sure. It has to do with I suppose if you look at the nature of the nuclear reactions, the neutrinos are balanced with the type of particle they are able to.
Dave, can you maybe unshare? Maybe we can see Steve.
Okay.
Thanks.
There we go.
Hi there. Yes, I mean it has to do with the nature of the reactions that are producing the neutrinos, and the fact that these different flavors, different types of neutrinos are sort of paired with the types of particles they're able to create. So electron neutrinos tend to be paired with electrons that are involved in the process, and muon neutrinos with muons. And muons are like heavier versions of electrons, and taus are even heavier versions of that. And just looking at sort of the energies and the types of reactions you can have in the sun, you just can't create along with it the partner muon or tau neutrino to create these other types of neutrinos. So just energetically, it's simply not possible. You always have to sort of create these things in this sort of paired kind of way. And so you can only do this with electrons because they're a light particle, and it's easy to make this reaction work in the sun.
Thank you. Another of the people attending the conference ask if neutrino may oscillate into antimatter. Are there more angles you have to look for? Dave, do you want to take this one?
Very good. You got us. Yes, indeed, there are. If neutrinos are their own antiparticles, if they're these Majorana particles, there are indeed two more angles that could potentially violate CP. And those are, in fact, the angles that would produce the matter-antimatter asymmetry in the universe. The unfortunate thing is it's extremely difficult to see how they could ever be measured in an experiment on Earth.
And Steve is trying.
No, well,
we're measuring a thing that we think that we have a chance of measuring right now, but there are other sort of phases that we don't see experimentally how to measure it yet. But I think, one step at a time. We try to sort of box things in and then look to sort of see.
But somebody was asking also about Majorana neutrino. Maybe you can expand a little bit about that, Steve.
Yeah, I mean, I think I tried to answer this in the chat. It is what I was talking about without naming it so. Majorana neutrinos are neutrinos that you can sort of flip between particle and antiparticle. So in some sense, they are their own antiparticle, but it just sort of the neutrinos, have amongst their bizarre properties is the direction of their spin relative to their direction of motion is always the same. It's always sort of left-handed. And so it's hypothesized, well, is that the only difference between neutrinos and antineutrinos? If you flip it around and make it right-handed, does it all of a sudden become an antiparticle? And so so that you would call a Majorana neutrino, as opposed to having distinct particle and antiparticle. It is the same, and you can just sort of flip it one way or the other.
Okay, we have a couple of questions that are related. And one of them asks where and how you're currently looking for the hypothetical fourth flavors of neutrino. And there were other questions that were asking about sterile neutrino, etc. Dave, do you want to take this one?
Yeah, so sterile neutrinos are sort of the experimentalist dream or nightmare, depending upon how you want to look at it. If ordinary neutrinos are hard to see, imagine a neutrino that doesn't even have weak interactions. And so it's essentially, you can't detect a sterile neutrino. All you can detect is whether the sterile neutrino, whether an ordinary neutrino disappears and turns into a sterile neutrino, so an oscillation not consistent with the other oscillations you expect to see, or just appears from nowhere as a sterile neutrino oscillates into it. The problem with them is that almost anything you get wrong in a normal neutrino experiment can be fit by assuming there's a sterile neutrino. And so if you take all of the different neutrino experiments that have been done, if you have a very large array of experiments, there will always be a few that will be sort of at the edge of their allowed regions, or maybe even outside of their allowed regions. And so it's possible to speculate that you can explain that by invoking sterile neutrinos. And once you've done that, the only way to test it is to do another experiment that's similar. And when we've tried to do that in the past, we have never succeeded in reproducing any of this. The only time that there has been a sort of a confirmation was when the LSND experiment at Los Alamos saw an excess of electron neutrinos from decay of stop pions. And then an experiment called Mini-Boon was done at Fermilab, which initially did not confirm these results, but after taking more data, saw another anomalous result, which could be interpreted as sort of, the two don't really fit each other, but something kind of halfway in between might fit them both. And so that was speculated to be sterile neutrinos. An experiment which I showed you, microboon, was done to look at that mini boon anomaly and see if it can reproduce it. And it has just released its results, and it failed to reproduce it. So that you can never kill off sterile neutrinos completely, because if you kill them in one place, they'll pop up in another. And so we can't say for certain that sterile neutrinos don't exist. And to be fair, they are a generic prediction of most models beyond the standard model. It's not that this is just something crazy experimentalists use to explain their data. It's something that theorists expect to exist. So if we were to find them, it wouldn't be that big a surprise. It's just that it's an excruciatingly difficult thing to do experimentally. And so far, we have never found a consistent pattern of experiments that, when repeated, gave the same results. So I fall back on a lesson my advisor taught me years ago. Science is not about what you can measure. Science is about what you can reproduce. And so far, we have been unable to reproduce any measurements of sterile neutrinos.
So one especially informed person actually asked, is sterile neutrino is the only way to explain the anomaly detected by LSND and mini boon? If it's not confirmed by microboon, what did they see in mini boon? The excess in mini boon was significant, I thought.
Well, by definition, if it's not sterile neutrinos, there is an explanation. We just don't know what it is. Yeah, I don't know is the answer. If I knew, I'd have told them a long time ago and saved everybody a lot of work. You always have to be concerned that it might just be instrumental. There might be something that the experiment was doing that just wasn't expected and wasn't understood that caused that. The anomaly is quite small. It's quite a small anomaly. It is possible there's something funny in the cross sections. It's hard to know what it could be. I mean, obviously, if it were easy to come up with some instrumental explanation, then we would have done it a long time ago. The short answer is we don't know. Okay. And so we will have to do more experiments. That's the way it works in science.
I think sort of pointing out, neutrino experiments are hard. And by definition, every time we do one, we sort of push the bounds of what we can say and can't say. And so we look for these things. And the other trick is that sterile neutrinos, like some other things, by definition, if they are beyond the standard model, we don't have guidance. And so there are, generic ideas here and there. And so we look where we can look and see if we can find something that can't be explained by something else, then maybe we're onto something. But as Dave sort of said very nicely, we need a consistent picture. We don't have that yet.
Yeah, just to add, I mean, there is a series of experiments at Fermilab that is called a short baseline neutrino experiment that will try to look at this oscillation and try to see, again, to answer maybe more directly some of these questions. But there is a very fundamental question from a couple of people. One is Will, and he's age 13. And we kept talking about CP violation, Professor Wark and Professor Biller. But what are you talking about? What is CP violation?
It is the rate at which, if neutrinos can flip into their own antiparticle, for example, in order to get an asymmetry, a sort of a difference, you need the rates of those to be different, whether you're flipping from one to the other, right? So in the direction, so that you can develop this. So that's sort of CP symmetry, that the rates will depend on whether you're a particle or an antiparticle.
Yeah. Basically, it's just that the laws of physics will not be quite the same for matter and antimatter. But if we said it in simple ways like that, then we couldn't justify getting big salaries. So we have to give it fancy, weird names. So we call it CP violation.
Yeah, that is a good answer. And again, it's really important that matter and antimatter behave differently, because matter and antimatter was expected to be created at the same rate at the Big Bang, and if it annihilates with each other at the same rate, we will not be here. Okay, so it's a very important asymmetry for all of us. Okay, so I have a few other questions that we would like to ask. So there is a question that goes into one of the details. Nova disagree with Super K, with T2K, about CP violation. So we need a bigger detector for both. But we are also continuing to understand the response of today's detectors while we wait for new ones to be built.
Well, that's a good question. The point is that we know these experiments, Nova and T2K, were designed to measure that third angle. That's what we built them for. And that's, so when you design an experiment, when you build its size, when you design the near detectors, which Oxford was very heavily involved in doing and built large parts of those near detectors, you make them sensitive enough to do the job that you need to do, because you don't have infinite money. So we built them to look for that third angle, and we know that no matter how big CP violation is, there's a limit to how big it can be. It can be maximally violated. That's it. It can't be more than that. We won't be able to get convincing, compelling measurements out of Nova and T2K. They're just not sensitive enough because they're not big enough. We just won't have enough events. And the systematic uncertainties are too great. In the case of both experiments, our ability to extremely accurately predict what we should see is just not good enough, because they just weren't built for that. So when, I've concentrated on the fact that the experiments are bigger because that's easy to explain. They're also better in ways that are more subtle, and the systematic uncertainties in the experiments will be smaller. There's a whole nother experiment in both of them, which I didn't discuss, which is a new type of near detector, which you can move off axis of the beam and measure the neutrino properties as a function of the off axis angle from the beam, which corresponds to measuring them at different energies. And by doing that, we'll be able to reduce our systematic uncertainties in both experiments by a factor of 5 below what they are now. So as well as getting thousands of events rather than the sort of dozens we have now, we'll understand them much better. So we don't wait for a couple of reasons. One is it takes about 15 years to build one of these things, and I'm 63. So I really don't want to wait very long, thanks. So that's one reason, but the main reason is we just know that we have to have these experiments. We won't be able to do it with the experiments we have. We know they're not good enough.
Okay, so now we are ready to wrap up. We will answer the question that you send us later on. But one more question to both of you before we close. What is the most fun, dangerous, exciting things that you have done while working on an experiment? Oh, quick answer, both for Dave and Steve, and then we close.
Oh, dear. Well, the most dangerous thing, I worked on an experiment in the former Soviet Union, and in a mine, underground in the former Soviet Union, and their safety standards would curl your toes. So I'm not going to tell you the most dangerous things that happened, because I'm not sure the statute of limitations is expired.
Okay.
The most fun is just working with really smart people on stuff you love to do, It beats working for a living,
Steve.
Yeah, it's always an adventure, these experiments. I started my career actually doing ground-based gamma ray astronomy, and so that was 2 kilometers up. And now I've been working for, you know, last sort of couple, you know, dozen years, 2 kilometers down. And when you go to these experiments, it's a bit like walking on the moon. You know, you put on this sort of garb and you go down this sort of, you know, it's into a, you know, it's a dangerous environment, and you walk to your lab and you come back up. And I remember, you know, it's warm down there, so deep that it's warm, and it being something like, you know, 40 degrees, you know, and then coming up into the dead of a Canadian winter at 40 degrees below. And so, but, you know, it's as Dave sort of said, it's just working with people in the camaraderie and going through all that is just you know, a load
and that is true for all of us. I think that part of being a physicist is sort of being an explorer and looking at new windows to understand and the universe and what is around us. Thank you so much, Dave and Steve. Big clap to everybody, and thank you for joining us in this spectacular journey to the understanding of the ghost particles. Thank you. Bye-bye.